So this is section 5.2, which is about the properties of rational functions. So rational functions are quotients of polynomial functions, which just means that they're a function that can be written as p of x over q of x, where p of x is a polynomial and q of x is a polynomial. A good example of this is f of x equals x squared plus 7x plus 9 over x times x minus 2 times x plus 5. This has a polynomial on top. P of x would be x squared plus 7x plus 9. And there's a polynomial on bottom. Q of x would be x times x minus 2 times x plus 5. And when we talk about rational functions, we've kind of talked about this before, but the domain of a rational function is that the bottom of it cannot equal 0. So in this rational function here, we would say x cannot equal 0, x minus 2 cannot equal 0, x plus 5 cannot equal 0. And we end up getting that x can't be 0, 2, and negative 5. If we were to try that in interval notation, it would be this really long string, negative infinity to negative 5, union, negative 5 to 0, union, 0 to 2, union, 2 to infinity. So, in order to find your domain restrictions, you really just need to look at the bottom of the rational function, set it not equal to 0, and solve. Okay, so let's look at example 1. Example 1 asks us to find the domain of the following rational functions. So we have f of x equals x squared minus 9 over x minus 3. So take the bottom, x minus 3, say it cannot equal 0. Add the 3 across, so you get x cannot equal 3. If we're to write that in interval notation, that would be negative infinity to 3, union 3 to infinity. Okay. Let's look at B. We got g of x equals x over x squared minus 9. So it's x squared minus 9 cannot equal 0. Add the 9 across, so it's x squared cannot equal 9. And then to get rid of the square, we would do a square root. And so we get x cannot equal plus or minus 3. Remember, when you take the square root, you have to have a plus or minus. So it means we actually have two restrictions. So when we write our domain, we're going to go from negative infinity until the first restriction, which is negative 3. Then we'll have a union, and we'll go from negative 3 to the next restriction, which was positive 3. And then we'll have union 3 to infinity. Okay? And so there is our interval. All right, letter C, we have h of x equals x plus 3 over x squared plus 9. So if we take the bottom, x squared plus 9, and set it not equal to 0, we'd move the 9 over, we'd say x squared cannot equal negative 9. Now, let me ask you a question. Is there any real number that you can square and get negative 9? No. There is an imaginary number that you could square and get negative 9. There's actually two of them. But when we talk about domains, we're only talking about real numbers. So there's no real number that you can square and get a negative 9. So this right here has no solution. And when that has no solution, our domain just remains negative infinity to infinity. Okay? And there are rational functions that have domains that go negative infinity to infinity. And that's okay. Alright, so that's all about domain. Next thing we're going to talk about is asymptotes. Okay? And to help us visualize asymptotes, we're going to start with the parent function of rationals, which is the reciprocal function. F of x equals 1 over x. The reciprocal function has a domain of negative infinity to 0 and union 0 to infinity. And it looks like this picture below right here. Now you might notice a couple of things, that as x approaches 0 from the left, the y value starts going down towards negative infinity. And as x approaches 0 from the right side, the graph starts going up towards positive infinity. That behavior is caused by what's called a vertical asymptote. There's technically a vertical line right here that the graph cannot touch. Okay? So there's just a space where the graph cannot touch that line. Okay? Similarly, as x approaches negative infinity, as x goes out here to the left, the y value, you notice, is getting closer and closer to 0. Over here, as x approaches positive infinity to the right, the y value is also approaching 0. This kind of behavior is caused by what's called the horizontal asymptote. So the horizontal asymptote guides the end behavior of the graph. It guides what happens out here at the far left and what happens out here at the far right. So as we go out to the left side, it's going to get closer to that green dotted line. As we go out here to the right side, it's going to get closer to that green dotted line. Okay. Now later on in these notes, we will talk about how we actually find these asymptotes, the vertical asymptotes and the horizontal asymptotes. But for right now, just understand that, if x is getting closer to a number and y is going to positive or negative infinity, you're going to have a vertical asymptote. And similarly, if x is going to positive or negative infinity and the y value is getting closer to a number, you'll have a horizontal asymptote. Alright. So let's start with talking about vertical asymptotes. So the line x equals a is a vertical asymptote of the graph if, as x approaches a, the f of x, the y value, increases or decreases without bound, which basically just means it goes to infinity or negative infinity. So I kind of put it in a little notation here. If f of x goes to plus or minus infinity as x gets closer to a, you have a vertical asymptote. So how do we actually locate these algebraically? Well, if your function f of x equals p of x over q of x is a rational function, and p of x and q of x have no common factors, then the bottom down here is going to create your vertical asymptote. So we kind of have a two-step process for locating vertical asymptotes. First off, cancel out any common factors between p of x and q of x, because those common factors do not create vertical asymptotes. Then whatever factors remain in the q of x in the denominator will cause vertical asymptotes. So let's look at that. So example 2 here asks us to find the vertical asymptotes, if any, of the graphs of each rational function. We're going to start by factoring. We can't really do anything on the top, so it's just x. But on the bottom here, x squared minus 9 is the difference of perfect squares, and factors into x plus 3 times x minus 3. Okay. Now, are there any common factors between the top and the bottom? No. So what that means is both of these factors are going to create vertical asymptotes. So x plus 3 is going to equal 0, x minus 3 is going to equal 0, and we'll get x equals negative 3 as one asymptote, and on this one we'll get x equals 3 as our other asymptote. So this particular rational function will have two different vertical asymptotes. All right, letter B, we have g of x equals x plus 3 over x squared minus 9. Again, the first step is to factor. So on top we have x plus 3, that doesn't factor. On bottom we have x plus 3 over x minus 3, because it's the difference of squares. Then we look for common factors between the top and bottom. There is an x plus 3 on top and bottom, so those can cancel out. And so what we really have is just 1 over x minus 3. So that factor that's left on bottom creates our asymptote. So we'd say x minus 3 equals 0. And so we'd have x equals 3. So this graph only has one vertical asymptote, one at x equals 3. Alright, letter C, we have h of x equals x plus 3 over x squared plus 9. The first step would be to factor it. X plus 3 does not factor. X squared plus 9 does not factor, so it already is factored. You cancel any common factors. Alright, well, there's nothing in common, so nothing to cancel. So whatever's left in the bottom would create vertical asymptotes. So we'd say x squared plus 9 equals 0. Move the 9 over, we get x squared equals negative 9. Again, when we talk about these things, we're talking about real numbers. are there any real numbers where when you square them, you get a -9? No, there are not. So since there aren't any solutions to this equation, that tells us there are no vertical asymptotes. And I am going to abbreviate vertical asymptote to VA, just so that way I don't have to write out the words vertical and asymptote. Okay? So it's not too bad to find vertical asymptotes. They're pretty straightforward. All right. Next thing is horizontal asymptotes. So y equals b is a horizontal asymptote for the function if, as x goes to plus or minus infinity, y gets closer to b. And you can kind of see in my shorthand, y gets closer to b as x gets closer to plus or minus infinity. Now, there are two different methods you can use to find the horizontal asymptotes. One requires the memorization of a list, the other requires the memorization of a process. It's up to you which one you want to do. It doesn't really matter to me as long as you do one of them. Okay? So if you're going to memorize the list, this is your list to memorize. Okay? If the degree of p of x is smaller than the degree of q of x, then y equals 0 is your horizontal asymptote. So what that means is if the degree on top is smaller than the degree on bottom, you're going to have y equals 0. B, if the degree of p of x is equal to the degree of q of x, then y equals a sub n over b sub n is the horizontal asymptote, where a sub n is the leading coefficient on top, and b sub m is the leading coefficient on bottom. So if the powers are equal on top and on bottom, you just divide the leading coefficients. And then C, if p of x is larger than q of x, if the degree on top is bigger than the degree on bottom, then there is no horizontal asymptote. So that's the list if you want to memorize it. Now if you don't want to memorize it, well then that's where this process that you see here in number 2 comes in. Okay. So here's some steps you can follow to find horizontal asymptotes. A, make sure that p of x and q of x aren't written as factors. Multiply them out as much as possible. B, divide everything by the x that has the highest power. Whatever x you see with the highest power, divide everything in the equation by that x. C, simplify the expressions as much as possible. Reduce things, cancel things out, all of that fun stuff. D, any fractions that are left over that have x in the denominator will go to 0. Your horizontal asymptote is whatever is left over. If you're just left with 0 on bottom, then that tells you you have no horizontal asymptote. Okay? And so I'm going to be using this process, but again, you could use this memorized list if that's what you'd like to do. Alright, so example 3 here asks us to find the horizontal asymptotes for these functions, if there is one. So part A, we have f of x equals 4x over 2x squared plus 1. The highest power I see is x squared, so I'm going to go through and divide everything by x squared. So 4x divided by x squared over 2x squared divided by x squared plus 1 divided by x squared. And then I'm going to simplify. Here, this x can cancel out one of the x's beneath it, so I end up with 4 over x. On the bottom, these x squareds can cancel, so I would just have 2 plus, on this last term on bottom, nothing cancels, so it's just 1 over x squared. Okay. And then as I said, any fractions that end up left over with x's on the bottom go to 0. So this fraction right here, because it has an x still on bottom, it's going to go to 0. This fraction right here, because it has an x on bottom, it's going to go to 0. So what I really have is 0 over 2 plus 0. So that's 0 over 2. 0 divided by 2 is 0. So my horizontal asymptote is y equals 0. And the more you do this process, the easier it becomes. It just takes a little bit of practice is all. Alright, B, we have g of x equals 4x squared over 2x squared plus 1. The highest power I see is x squared, so I'm going to divide everything by x squared. So 4x squared over x squared over 2x squared over x squared plus 1 over x squared. Simplify it. On top, the x squareds cancel out, and I just have 4 left over. On bottom, for this first term, the x squareds cancel out, and I just have a 2. Plus, in the second term, nothing cancels out, so I just have 1 over x squared. Any fractions that remain with x in the bottom go to 0. So this fraction right here is going to go to 0. So I'll have 4 over 2 plus 0. So that's 4 over 2. 4 divided by 2 is 2. So y equals 2 is my horizontal asymptote for that function. Alright, letter C. We have h of x equals 4x cubed over 2x squared plus 1. The highest power of x I see is x to the third power. So I'm going to divide everything by x to the third power. So 4x to the third over x to the third over 2x squared over x to the third plus 1 over x to the third. And we'll clean it up. On top, the x to the thirds can cancel out, and so I just have a 4. On bottom, for this first term, 2 of these x's on top can cancel 2 out on the bottom, so you'd end up with just 2 over x plus 1 over x cubed. That really can't simplify at all, so it's just 1 over x cubed. Now that we've simplified, any fractions that still have x on the bottom are going to go to 0. So this is going to go to 0, and this is going to go to 0. So what I really have is 4 over 0 plus 0, which is 4 over 0, which is undefined. And when I get that undefined answer, that tells me I have no horizontal asymptote. And we do abbreviate horizontal asymptote HA, just because it's a little shorter to write than horizontal asymptote. Okay. Alright. There is another kind of asymptote that we sometimes see with these graphs, and it's called a slant asymptote or an oblique asymptote. Different textbooks use different wording, but whether it says slant or oblique, it kind of means the same thing. So a slant asymptote happens when the degree on top is exactly 1 higher than the degree on bottom. So like if we have an x cubed on top and we have an x squared on bottom, that tells us we're going to have a slant. Now, how you find the equation of the slant asymptote is by either long division or synthetic division. When you do these divisions, you ignore the remainder, because as x goes to positive or negative infinity, that remainder will go to 0, go away. Okay. And so you can kind of see here, here's a graph of one that has a slant asymptote. F of x equals x squared plus 1 over x minus 1. The degree on top is 2, the degree on bottom is 1, so this is exactly 1 power higher than what's on bottom, and so it generates this slant asymptote, which is just a diagonal line here at x plus 1. Okay. So let's find some slant asymptotes. Example 4 asks us to find the slant asymptote of f of x equals x squared minus 4x minus 5 over x minus 3. And so we're going to do long division. I have x squared minus 4x minus 5, and I'm dividing by x minus 3. What would I need to multiply x by to get x squared? I would need to multiply by x. X times x is x squared. X times negative 3 is negative 3x. And then I do a subtraction. X squared minus x squared those cancel out. Negative 4x minus a negative 3x, just so you can see it. Negative 4x minus a negative 3x. You have minus a negative, so it really means it's plus. So negative 4x plus 3x gives us negative x. Then just like with old school math, you drop down the next term. So bring down that minus 5. Okay. What do I need to multiply x by to get a negative x? A negative 1. Negative 1 times x is negative x. Negative 1 times negative 3 is positive 3. And then we subtract. Negative x minus negative x, those cancel out. Negative 5 minus 3 is negative 8. Now this number that we get at the end is the remainder. And as I said just a minute ago, we ignore the remainder. It doesn't really matter. So up here on top is the equation for our slant asymptote. Our slant asymptote is going to be at y equals x minus 1. Okay there? Okay, let's look at our last example. So our last example asks us to find the slant asymptote for f of x equals 2x squared minus 5x plus 7 over x minus 2. So again, we're going to do long division. We have 2x squared minus 5x plus 7, and we're dividing it by x minus 2. What do I need to multiply x by to get 2x squared? I need to multiply it by 2x. 2x times x is 2x squared. 2x times negative 2 is negative 4x. And then we subtract. 2x squared minus 2x squared, those cancel out. Negative 5x minus a negative 4x. So again, just so you can see it, this is what we have. Negative 5x minus a negative 4x. Minus a negative really means it's plus. So negative 5x plus 4x gives us negative x. And then we drop down to plus 7. Alright, what do we need to multiply x by to get a negative x? A negative 1. Negative 1 times x is negative x. Negative 1 times negative 2 is a positive 2. And then we subtract. Negative x minus negative x, those cancel out. 7 minus 2 is 5. That number right there of 5 is our remainder. And remember that the remainder really doesn't matter. All that really matters is our answer up here. So our slant asymptote is at y equals 2x minus 1. Okay. And so that's it for this section of notes. Just make sure you understand how to find domain of rational functions and how to find the 3 different types of asymptotes, because it will be very important for our next session. As always, if you have any questions, please feel free to shoot me an email.